Hey audience, last time I built a prototype logic chip tester. I was going to abandon the project when it failed to test some chips, but I've recently figured that out, so I'm going to finish this up. Someone pointed out in the comments, thank you by the way, that all the switches could be checked by a single pin, and an analog pin at that, which means that now we can use A6 or A7, which are otherwise unusable in this project since they're not digital I/O pins. And that frees up 2 more digital pins on port C for testing. There are lots of different ways of doing this, but what I settled on was this. It's a voltage divider that evenly divides the supply voltage into equal drops. Then each switch connects one of the voltages to the analog input. This won't let us detect multiple buttons being pressed at once. There are other methods that will, but they were either too complicated or required lots of different resistor values, and I like to use the same resistor value everywhere when possible. Pressing more than one button at a time isn't important for this anyway, which I talked about in the last video. Also, since the LED display has a controller that we talk to over I2C, I was curious if whatever controller was used could also scan for switches and report back over I2C. And sure enough, it can. Turns out it can drive up to 128 LEDs and scan for up to 39 switches. So it would definitely be possible to remove all the push-button code from this project with this controller. But this display board is what I happen to have, so we're stuck with it for now. And that gives us 18 pins to control. But I haven't seen any 18-pin DIP chips. I've seen plenty of 16 and 20-pin chips, but for some reason 18-pin DIPs don't seem to be that common. So this really won't be useful unless we can have just 2 more pins. So if you remember, pin C6 was also the reset pin. That would give us 1 more pin, but what about port B? Only 6 port B pins are present on the Arduino, but the datasheet shows that there are 8 I/O pins on port B. So what gives? So I've been treating the Arduino as basically a breakout board for the Atmega 328P, but there's a bit more to it than that. The Arduino board also has a 16 MHz crystal for the clock, and the same way that pin C6 is also the reset pin, pins B6 and B7 are also pulling double duty as the pins that the crystal is attached to. And they aren't broken out onto I/O pins from the Arduino because those pins are always used for the crystal. The Atmega 328 also has an internal 8 MHz oscillator that can be selected by changing some of the fuse bits. It's not as accurate as a crystal oscillator, but it doesn't need to be for this. So we can switch to the internal oscillator and then solder some wires onto those pins to get 2 more digital I/Os. We'll have to program through the ISP interface after changing the clock to one with half of the expected frequency, but I've gotten used to that with my signal generator project, and we have to use the ISP interface to set the fuse bits anyway. You could probably create a new board type for the Arduino IDE to expect a halved baud rate, or you could modify the bootloader, but that's not important to me right now. I wanted to just solder onto the pins of the Atmega and leave the crystal on the board just in case I wanted to reuse the Arduino for something else, but that went poorly. And I'm not likely to desolder and reuse this, so I took the crystal off and then soldered to its pads instead of to the pins on the chip. Pro tip, change the clock select fuse bits before removing the crystal. I had to get the tweezers out and solder this tiny surface mount crystal back on. I also had a fun little software bug when I changed from 16 pins to 20 pins. I shift a 1 into position when building a bit mask from a string, and I thought I'd be safe by changing my 16-bit integers into 32-bit integers to accommodate the 4 new pins. But as it turns out, in this sub-expression, the 1 is treated as type int, which on most modern platforms is 32 bits, but for GCC's AVR compiler it's only 16 bits. The C standard only specifies that an int must be at least big enough to hold a 16-bit int. So even though the 1 is a constant and the result goes into a 32-bit variable, this 1 sub-expression was being truncated to 16 bits and returning 0 when I shifted by 16 or more bits. I had to use a larger value of 1 to fix this. This is one of the very few things that I don't like about the C language. But anyway, this is something that I run into a lot when writing code for microcontrollers, so I thought I'd bring it up in case it helps anyone else out there. As with the capacitance meter I made a while ago, a lot of the decisions that I made here are not decisions that I would make if I were designing a product to sell. For instance, the logic levels are technically incompatible going from TTL to CMOS, or at least they can be, so sensing the outputs of a chip I'm testing isn't really guaranteed to work. There also might be issues with the Arduino I/O pins not being able to source or sink as much current as some TTL chips expect, even though that's unlikely when the CMOS inputs don't draw any current from the TTL chip's outputs. And then, of course, there are the rise and fall times that I've already run into trying to test the 74F109. But this is good enough for most of the chips that I'll be testing. And if I run into problems with the assumptions I've made, it'll give me false negatives, telling me that the chips failed when they aren't actually bad, which is much better than false positives, telling me that the chips passed when they should have failed. Lies are okay with me as long as they're overly cautious lies. Now I just need to add more tests. I'll probably test chips as I use them and add tests only when I actually use the chip for the first time. So if I want this thing to really be complete, I'll need to do some more projects. I'll see you then.